Imagine you have a relatively straightforward task to complete. Let's say you need to deep clean your entire house, right?
Right, which usually takes, what, maybe an hour or two if you just put your head down and do it yourself?
Yeah, exactly. But because you love efficiency and you happen to have this massive budget, you decide to hire a team of 22 professional cleaners to come in and do it for you simultaneously.
I mean, that sounds like a dream, honestly.
Right, you'd think so. So you open the front door, let all 22 of them inside, and you just step back to watch the magic happen. But instead of taking a few minutes, the job ends up taking 35 hours.
Oh, wow.
Yeah. Why would hiring 22 people to do a job take 35 times longer than just doing it yourself?
It sounds like this bizarre riddle,
Yeah.
because you naturally assume more hands make less work.
Right.
But in the architecture of modern systems, especially when we're talking about computer science, this scenario is a very real and honestly very frustrating reality.
Well, welcome to the deep dive. Today, we are exploring a really fascinating presentation from 2026 by developer at Luck036. It's titled ST versus MT, Parallelizing Polynomial Root Finding.
It's a great piece of work.
It really is. And for you, the listener, our mission today is to explore the sometimes deeply counterintuitive world of software engineering. We're looking at a scenario where a developer tried to make their code run faster by making it multi-threaded, which basically means forcing the computer to execute multiple instructions at exactly the same time.
Right. The goal was pure speed.
Yeah.
But the result was, well, a spectacular backfire.
A total backfire. And the stakes here go way beyond just, one piece of code.
Oh, absolutely. We live in a world that is just obsessed with doing everything in parallel. We go to the store, we buy laptops with 8, 16, 22 cores.
Right, because bigger numbers are better.
Exactly. We operate under this assumption that faster, more parallel hardware automatically guarantees faster results. But this source material is an absolute masterclass in why that assumption is fundamentally flawed.
Yeah, it shows how the invisible friction of managing a team can actually it can halt progress completely.
It really can.
So before we can solve the mystery of this massive slowdown, we have to understand what this developer was actually trying to achieve, like on a mechanical level.
Right. We need the context.
So the original goal was finding the roots of polynomials. They were using a C++ library called GingerCrep and looking specifically at two mathematically intensive methods.
Right.
There's Baer-Stow's method, which is designed to find quadratic factors, and then the Aberth-Ehrlich method, which finds complex roots simultaneously.
And to visualize this, without getting totally lost in the advanced calculus, finding a polynomial's root essentially means finding the exact values where the equation's curve crosses zero on a graph.
Okay, so it's a very specific point.
Exactly. And it is not something you just calculate once. It's a highly iterative process.
Right, lots of repetition.
Yeah. The computer makes an educated guess, runs that guess through a massive equation, updates the guess based on the error, and repeats that loop over and over until it zeroes in on the perfect answer.
And when you have a complex polynomial, you have multiple roots to find, which means you have to run that looping guess and check process many, many times.
Precisely.
Okay, let's unpack this. If you have a massive equation and you need to find, say, 24 different roots, the strategy the developer used initially makes total sense.
It's totally logical on paper.
Right. They thought, hey, I have multiple roots to find. I happen to be running this on a beast of a machine with 22 processing cores.
Very nice machine, yeah.
So they figure, I'll just assign one calculation task per root and tell the computer to run them all at the exact same time, one thread per root. From a layman's perspective, that sounds like a slam dunk for efficiency.
It is the ultimate intuition trap. If I have 24 things to do and I have the physical hardware to do them all at once, you'd think it should be done in a fraction of the time.
Right.
But the benchmark results the developer recorded revealed a complete disaster.
Disaster is honestly putting it mildly. They tested this parallel approach on two specific math problems. First, a FIR degree 48 polynomial, which requires finding 24 roots.
Right, a bigger problem.
And second, a smaller degree 8 polynomial, which only has 4 roots. For both of these tests, the multi-threaded approach, the MT approach, was just absolutely crushed by the traditional single-threaded or ST approach.
The numbers are frankly staggering when you look at the raw microseconds.
Let's look at that degree 8 polynomial, the one with just 4 roots. Using the Baer-Stow method, the multi-threaded version was 23 times slower.
23 times?
Yeah. The computer, just thinking linearly, one step at a time, took 14 microseconds. The multi-threaded version took 334 microseconds.
And depending on the algorithm variant they threw at it, the penalty was even more severe.
It was. The Bairstow AutoCore method was 24 times slower, and the Aberth method, a staggering 35 times slower. Yeah, the single-threaded Aberth solved the problem in 17 microseconds. The 22-core multi-threaded beast, 583 microseconds.
It's just wild.
If I'm cooking a complex dinner for you, and I hire 22 professional chefs to help me make 4 dishes, how on earth does it take 35 times longer than if I just cooked it by myself? Is the computer just tripping over its own feet here?
That's fascinating here is the mathematical reality of negative scaling.
Yeah.
Normally, you expect scaling to be a multiplier greater than 1.
Like maybe 22 threads gives you an 18x speed up because of some minor friction?
Exactly. But here, they were seeing something like a 0.5x speed up. The system isn't just failing to scale gracefully. The very act of attempting to distribute the work is actively destroying the performance.
That is wild.
To use your analogy, the 22 chefs aren't just bumping elbows in the kitchen. They're spending so much time putting on their aprons, meticulously washing their hands, and holding meetings about where the salt is located, that the food in the oven has completely incinerated.
That is a great image. So the intuition is completely shattered. We have our crime scene. The code is running at a glacial pace. How did the developer isolate exactly what was going wrong inside the system?
Well, they had to perform a deep autopsy on the code. They broke down the exact life cycle of a single thread. And the first massive bottleneck they discovered was the per-task administrative overhead.
Okay, let's talk about what that actually means in C++ Belai. To tell a processor to do something in the background, the code uses a function called pool.onQ.
Right. And pool.onQ is not a magical portal that just teleports math to a processor.
I wish it was.
Don't we all? But on a Windows operating system, creating a task requires a lot of bureaucratic paperwork under the hood.
Like what kind of paperwork?
Well, first, the system has to allocate memory on the heap. That means scanning the computer's RAM to find an empty parking spot for the data.
Okay.
Then it has to lock the thread so no other process can interfere with it. Finally, it has to make a system call.
And a system call is a pretty big deal, right?
Oh, yeah. It literally means pausing the program, crossing over into the Windows kernel, asking the operating system for permission to use hardware resources, and crossing back.
And according to the presentation, that whole bureaucratic process takes about 1 to 5 microseconds, which to you and me, I mean, that sounds instantaneous.
It does, right? Until you look at the actual computational work being assigned, the math required to calculate a single root iteration only takes about 3 microseconds.
Wait, if the actual calculation takes 3 microseconds and assigning the work takes 5 microseconds, we're spending more time managing than working.
Precisely. If we look at that degree 8 polynomial, which has 4 roots and takes 6 iterations to solve, the code is triggering 24 heap allocations, 24 locks, and 24 system calls.
That's just exhausting to even think about.
It is. And if we connect this to the bigger picture of high-performance computing, time is highly relative. If you're rendering a 3D movie and the task takes an hour, a 5 microsecond delay to set up the task is totally irrelevant.
Right, a drop in the bucket.
But if your actual productive work is microscopic, that management delay is catastrophic. You're spending upwards of 60% of your total CPU cycles just delegating tasks.
Delegation destroying productivity. I think a lot of middle managers listening can deeply relate to that.
I'm sure they can.
But even if a thread finally gets through that administrative bottleneck, the presentation points out that it immediately hits a wall with how it handles memory. There was this massive flaw in how the system was copying data.
Yes. This revolves around a specific function in the library called Horner, which is used to perform synthetic division on the polynomial.
Right.
The original logic was designed to function in place. In software terms, that means it doesn't create a new output file. It just overwrites the original data as it does the math.
But if 22 threads are all trying to read from the original data simultaneously, and the Horner function is actively mutating and destroying that data while it works, I mean, you have a massive problem.
Exactly. To prevent the threads from completely corrupting everything, the system was forced into a defensive posture.
So what did it do?
It had to constantly make fresh, independent copies of the entire coefficients array for every single root, for every single iteration.
Wow. The scale of the waste here is mind-blowing when you add it up. For that larger FIR degree 48 polynomial, the system had to physically copy 392 bytes of data per root.
Which adds up fast.
It does. Multiply that by 24 roots, and the computer is copying 9.4 kilobytes of data per iteration. Across the whole process, that is 144 separate copies being generated in the machine's memory.
And the absolute worst part, All of that data is immediately thrown away the millisecond. The Horner function finishes its 3-microsecond math problem.
The hardware's memory bandwidth was essentially being choked to death.
It really was.
It's like photocopying a 100-page operational manual just so you can read one single sentence on page 42 and then tossing the entire manual into a paper shredder and then doing that 144 times a second.
It is the literal definition of memory thrashing.
Mm.
The processor cores are incredibly fast, but they're sitting there idle, twiddling their thumbs, waiting for the RAM to finish photocopying that manual.
So we have bureaucratic overhead and we have the great photocopying disaster. But there was a third issue the developer found, and this one sounds genuinely dangerous. Data races.
A data race is perhaps the most feared phrase in parallel programming. The presentation noted that the original code lacked a mutex, a mutual exclusion lock, and it didn't take a safe snapshot of the data before it started calculating.
Meaning the threads were just wildly running into each other.
Yes. In a multi-threaded environment, if thread A is trying to read a variable at the exact microsecond, thread B is actively overwriting that variable, you get undefined behavior.
That sounds bad.
It's terrible. Thread A might read the first half of the old number and the second half of the new number, resulting in a Frankenstein value that doesn't actually exist. The math becomes complete chaos.
But the developer noted that this code was actually producing the right answers, seemingly by magic. Why didn't it just crash?
Because of the specific hardware architecture they were using. They were running this on by 8664 processors, which happen to have a very strong memory model.
Okay, so the hardware saved them.
Basically, yes. The hardware itself essentially put up invisible guardrails that accidentally masked the software's error. If they had compiled this exact same code and run it on an ARM processor like a modern Apple Silicon chip, it likely would have imploded. The logic itself was a ticking time bomb.
Wow. To bring back our kitchen analogy, a data race is like those 22 chefs all trying to aggressively season the exact same pot of soup at the exact same time without communicating at all.
Yes, exactly.
One is dumping in salt while another is scooping it out. It's a miracle the soup was edible at all.
That is a perfect visualization. The threads were totally blind to each other's actions.
Okay, so we've isolated the 3 fatal flaws. The administrative overhead of creating tasks is taking longer than the math itself. The memory bandwidth is being choked by disposable data copies, and the underlying logic is a chaotic data race waiting to crash.
That's the crime scene, all right.
So how do you solve this? If the tax for assigning a single root is just too high, how do we start paying that tax without abandoning parallel processing entirely?
Well, you have to change your entire philosophy of how work is distributed.
Yeah.
You can't just patch a line of code here or there. You have to fundamentally reorganize the factory floor.
Which brings us to the developer's first major architectural shift. Batch scheduling. Instead of assigning one task per root, they shifted to one task per chunk of roots.
This is a highly elegant solution to the administrative bottleneck. If we look at the FIR degree 48 polynomial again, we have 24 roots to solve.
Right.
Instead of firing off 24 individual tasks and paying that 5-microsecond system call tax 24 times, they bundled the work. They reduced it down to just 4 overarching tasks.
Meaning they only utilize 4 of their 22 threads. And they handed each of those 4 threads a batch of 6 roots to process sequentially.
Exactly. You still maintain a high level of parallel processing. I mean, 4 things are happening at once, but you have just slashed your administrative bloat by a massive factor. You only ask the Windows kernel for permission 4 times instead of 24 times.
It's like, instead of handing a chef one single carrot to chop, making them wash their hands, and then handing them a second carrot, you just hand them the entire bag of carrots at once.
And let them work uninterrupted. It dramatically increases the ratio of productive computation time to administrative setup time.
But chunking the work didn't solve the data races, the chefs seasoning the soup at the same time. To fix that, the presentation details a shift from a Gauss-Seidel iteration to a Jacobi snapshot iteration.
Right.
What is the actual mechanical difference there?
This is where we get into how data flows through a parallel system. The original method was mimicking a Gauss-Seidel iteration.
Okay.
In mathematics, that means as soon as you calculate a new, better guess for a root, you immediately write it to the shared pool, and the next calculation uses that live, updated value.
Which is perfectly if you're just one person doing math on a piece of paper, right? Because
Yeah.
you always know what the latest number is.
Right. In a single-threaded environment, Gauss-Seidel is incredibly fast and efficient. But in a multi-threaded environment, reading live, constantly updating values is what causes those chaotic collisions. You're trying to read a number while someone else is actively erasing it.
So how does the Jacobi method fix that?
Well, a Jacobi iteration mandates a strict separation between reading and writing. At the start of the mathematical loop, the system takes a clean static snapshot of all the current root values.
Just freezes it in time.
Exactly. All of the active threads read from that frozen snapshot. They go off, do their complex math in total isolation, and formulate their new answers.
Okay, that makes sense.
And only when every single thread has finished its homework do they collectively update the live data pool all at once.
It completely eliminates the collision. It's like taking a high-resolution photograph of the recipe, printing out a copy for everyone, and locking the original in a safe. No one is fighting over the cookbook anymore.
Yes. And a fascinating byproduct of implementing this batch scheduling and snapshotting is that it fully exposed the hidden array corruption bug in that Horner division function we talked about earlier.
Oh, right, the in-place mutation bug.
Yes, because they were originally running one task per root. The fact that the function destroyed the data didn't immediately break the program. It just forced all that wasteful photocopying.
Ah, I see.
But once they batched the roots, meaning a thread had to process 6 roots in a row, the second root in the batch would try to read the data, only to find the first root had completely corrupted it. The program finally broke out in the open.
Forcing them to rewrite how the coefficients were passed, ensuring each thread got a dedicated, safe array to work with that didn't require constant, frantic copying.
Exactly.
That is a great example of how fixing one structural issue forces you to clean up the underlying hygiene of the code. But out of all the fixes, the one that really stopped me in my cracks was the sequential bypass.
This is the most philosophically profound change they made.
The developer instituted a rule for small problems, specifically polynomials with 4 roots or fewer. The multi-threaded function doesn't even try to be multi-threaded.
It just bails on it.
Yeah, it completely skips the thread pool. No heap allocations, no system calls, no mutexes. It just routes the math straight to the single-threaded processor. Here's where it gets really interesting. If you write a multi-threaded function, and your solution to make it faster is to literally turn off the multi-threading, are you just admitting defeat?
This raises an important question about our obsession with technology for technology's sake. We often confuse the tool with the outcome. The primary goal of a software engineer isn't to use 22 threads. The goal is to execute the calculation as fast as physically possible.
Right. It's about the result, not the method.
Exactly. What the developer realized through this painful exercise is that for very small mathematical problems, the bureaucratic setup time for parallelization will always mathematically exceed the computation time. There is no getting around the physics of a system call.
That's a hard limit.
It is. By implementing this sequential bypass, the developer transformed a rigid multi-threaded function into an intelligent auto function.
It became self-aware.
In a sense, yes. The code now actively assesses the sheer volume of the workload before it commits to a strategy. It looks at a 4-root polynomial and says, you know what? This job is way too small to justify assembling a team. I will just do it myself.
So with the factory floor completely reorganized, batch scheduling implemented, Jacobi snapshots preventing data races, memory hygiene cleaned up, and the intelligent sequential bypass in place, what does the final scoreboard look like? Did this rescue mission actually work?
The transformation of the benchmark data is remarkable. Let's look back at those small problems, like the degree 8 polynomial, which previously took a 35x performance hit.
Because of the sequential bypass routing it away from the thread pool, the new system was 27 to 29 times faster than the old, broken, multi-threaded version.
That's a massive leap.
It is. It essentially runs exactly as fast as the single-threaded baseline now. It stopped punishing itself for trying to be overly clever.
And the gains on the larger workloads are where the real victory lies. For the FIR degree 48 polynomial, the multi-threaded birth time plummeted from 4.0 milliseconds down to 1.37 milliseconds.
That is a 2.9x speedup over the broken version.
It is a massive reclamation of wasted time. Now, the source does note a caveat here. This optimized multi-threaded version was still slightly slower than the purely single-threaded version on this specific processor.
Wait, why is that if they fix all the overhead?
It comes down to the math itself. Remember how we discussed the Jacobi snapshot method preventing data races?
Yes, freezing the data so everyone can read safely.
While Jacobi is incredibly safe for parallel threads, mathematically it converges on the final answer slightly slower than the chaotic Gauss-Seidel method. So they traded a tiny bit of mathematical efficiency for a massive amount of architectural safety. It's a calculated compromise.
Okay, that makes perfect sense. Now, the presentation doesn't just isolate this to C++ then, it actually brings in a comparison to the Rust programming language, which I found fascinating because it speaks to how different ecosystems handle this exact same friction.
It is a crucial comparison. The C++ implementation relied on std.future, which uses a fairly naive, centralized thread pool.
What does that mean in practice?
That means there's one giant queue of tasks, and all the threads are constantly fighting and locking each other out to grab the next task from the center.
Which creates a bottleneck. So, how does Rust handle it differently?
Rust utilizes a fundamentally different architecture called Rayon work stealing. In a work stealing system, there's no giant central queue that everyone fights over. Instead, every single worker thread gets its own private queue of tasks.
Okay, so no fighting at the center. But what if one thread finishes its private queue early and just stands there doing nothing?
That is where the stealing comes in. If a worker finishes its tasks, it looks at the queues of the other busy workers, and it secretly steals a task from the back of their queue.
Oh, wow. That's clever.
It really is. Because it steals from the back while the busy worker is pulling from the front,
Right.
they don't collide. They don't have to lock each other out. It is a brilliant way to keep every processor utilized without the massive administrative bloat.
And did the benchmarks reflect that?
They did. The presentation notes that even before optimization, the Rust version only suffered a 1.5x penalty on the FIR48 polynomial, compared to the massive 6.2x penalty in C++.
That architectural difference is huge. But the source makes it clear that even with Rust's elegant work stealing, the core laws of physics still apply, right? Like, if the actual computation is microscopic, the overhead of moving it around will still bite you.
Absolutely. The language might change, but the math of negative scaling does not.
So let's synthesize everything we've uncovered from this presentation into some actionable lessons. The first one seems blindingly obvious in hindsight, but it's clearly ignored measure before optimizing.
Right.
The developer didn't realize they had a 35x slowdown until they actually forced the system to benchmark itself. The failure was hiding in plain sight.
And the second core lesson is understanding that thread pools are never free. Every single time you delegate a task to a background process, you are paying a tangible tax in memory allocations and system calls.
Which naturally leads to the third lesson: batch your tasks. If you have to pay a tax every time you cross a toll booth, don't drive 24 separate cars. Put everyone in a bus, group the tiny calculations together to maximize the productive work.
Fourth, snapshots are the antidote to data races. If you have a shared resource, you cannot let multiple workers read and edit it simultaneously. You must separate the reading phase from the writing phase.
Fifth, let the data flow logically. Design your system so that your functions aren't secretly mutating and destroying the data they're supposed to be analyzing, which chokes your memory bandwidth with useless copies.
A very expensive mistake to make.
Exactly. And finally, the ultimate realization, the absolute best optimization technique is knowing when to do nothing at all. Which brings me to this. So, what does this all mean?
It's the big question.
Right. We just went on a massive, highly technical journey into the weeds of memory allocation and algorithms just to arrive back at the conclusion to do it the simple way. If larger problem sizes, like degree 200 polynomials or shifting to massive GPU acceleration, are the only places where this multi-threading truly shines, why did the developer even bother studying these small polynomials so intensely?
Because examining failure at the micro level is the only way to expose the invisible friction within a system. Benchmarking those small degree 8 polynomials wasn't a waste of time. It was a vital diagnostic stress test. It allowed the developer to discover the exact mathematical threshold where system complexity stops being an asset and actively becomes a liability.
That makes a lot of sense.
If they had only tested massive degree 500 polynomials, the sheer weight of the math might have masked the administrative bloat. They might have achieved a minor 10% speedup, patted themselves on the back, and walked away entirely satisfied.
Never realizing that their underlying thread management was disastrously inefficient.
Exactly. By pushing the system on small tasks until it actively broke, they learned exactly how the gears of the machine actually work, and because of that, they built an architecture that scales intelligently rather than blindly.
You literally have to break the machine to figure out what the gears are actually doing.
Love that.
Yeah,
And for you listening, that is the ultimate takeaway to carry with you today.
for sure. True expertise isn't about forcing complex, cutting-edge tools onto every single problem you encounter. Expertise is having a deep, fundamental understanding of the exact hidden costs of the tools you are wielding. As we've seen, having a massive 22-core machine at your disposal is completely useless if the administrative overhead of managing those cores crushes the actual work you were trying to do.
And I think it's important to recognize that this dynamic isn't just about C++ code or finding the roots of polynomials.
No, not at all.
This is a fundamental human systems problem. I would encourage you to think about the multi-threading happening in your own life, your own household, or your own organization.
How often do you introduce a new, highly complex productivity tool, add a new layer of middle management, or deploy a sophisticated new AI assistant to your workflow, only to quietly realize that the administrative overhead of managing that new system takes longer than the actual work you were originally trying to do?
Exactly. Are your 22 chefs actually cooking, or are they just holding meetings about where the salt is?
Such a great way to look at it.
So the next time you try to drastically parallelize your life or your team's workflow, take a step back and ask yourself the hard question. Are you actually speeding up the computation, or are you just multiplying the overhead?